Hi, everybody. Welcome back. If we have sound problems again or any other problem, please let me know by chat to make sure that we don't miss anything interesting. This class will be our last class discussing welding processes. We have discussed welding arc welding processes in quite a bit of detail, and last class we discussed beam welding processes, laser beam welding, electron beam welding, and then we started to talk about using electric resistance as a source of heat, and we talk about resistance spot welding, the way we make cars, some like related processes that share the same fundamental principles. And we talked about some of the features of these resistance welding processes and some characteristics. And here's where we stopped last class. What I want to do now is to show you the video of the Society of Manufacturing Engineers about resistance spot welding, so you get a better sense. This video should have audio. Please let me know if it doesn't come through.
Resistance welding processes produce coalescence of overlapping workpieces with heat generated by the resistance of the workpieces to the flow of electric welding current and the application of pressure. Resistance welding is primarily used to join sheet metal stock, but is sometimes used to join thin plate. All metals which can be fusion welded are weldable by resistance welding. Resistance welding processes use copper electrodes. These electrodes perform four functions. They conduct the welding current to the work and, in some cases, fix the current density in the weld zone. They transmit a force to the workpieces. They dissipate some heat from the weld zone. And they maintain relative alignment and position of the workpieces in some resistance welding operations. Very high electric currents are used to quickly produce the resistance heat necessary for fusion. The three principal types of resistance welding are spot welding, seam welding, and projection welding. Spot welding refers to making welds one at a time between the electrodes. One, several, or many individual spot welds may be required, depending on the application. Spot welding, with the electrodes maneuvered by articulated arm robots, is commonly used to join sheet components of automobiles. In seam welding, coordinated pulses of electric current from rotating wheel electrodes produce a series of overlapping spot welds, resulting in a leak-tight welded joint. In projection welding, the welds are localized at predetermined points by projections, embossments, or intersections. Several points may be welded simultaneously. All resistance welding methods use either semi-automatic or automatic systems. With semi-automatic machines, the operator either positions the workpieces between the electrodes or positions a portable welding gun around them and pushes a switch to initiate the weld. Welding then proceeds according to a pre-programmed sequence. Automatic machines feed workpieces into the machine, where they are welded and then ejected without operator assistance. The typical resistance welding system consists of a control panel, a welding machine with a rigid frame, a low-voltage, high-current welding transformer, electrodes, leads connecting the electrodes with the welding transformer, controls to regulate electric current, and a pneumatic cylinder or other means of exerting force to the upper electrode arm.
All right, awesome. So a couple questions here. Let's start with an easy one. What do you think the electrodes in resistance spot welding are consumable or non-consumable? I'm watching the chat here. Yeah, thank you. Non-consumable. Yes, yes. And I want to be clear, in welding, when we say something is non-consumable, does not mean that does not get consumed. It means does not mean to be consumed. For example, in the case of TIG, the TIG electrode is a non-consumable electrode. Yet anybody who has welded with TIG knows that, yeah, it gets consumed all right. It's just not meant to be consumed. In MIG, yes, it gets consumed intentionally because we melt it on purpose. Good, so we're super on the same page. This is great. A more difficult question. Some of you might remember when we talked about stud welding, in which like a little piece is welded to a substrate. And now that you're talking about projection welding, and they were welding little pieces to a substrate too. But resistance projection welding is very different than stud welding. It's very different than, why, can anybody help me with what the difference is? I was talking about stud welding when we have, or flash welding. That's the word we use, flash welding. How is flash welding different than projection welding? We can weld studs with both, by the way. Okay. Oh, thank you. Yes, absolutely. Here I have an answer, and it's that flash welding involves an arc, and it's the arc what melts the metal, and then you put it together and it stays welded. And in projection welding, there is no arc. It's the electric resistance, the one that creates the melting. Thank you. So we're doing super, super well. Okay, I want to show you a super cool video about resistance spot welding. It's a very old video, and it's gonna show that it's old, but it's an uncommon video in which we are gonna see resistance spot welding as it happens. So let me play it for you. All right, look, this video, which I'm gonna play again in a second, says so much. This was a very difficult video to make because the way it was made, they cut the electrodes in half lengthwise, and then they cut the plate, the sheet also, it's in half, and everything had like a half plane that was visible. You never get to see that, right? This is, you're not meant to weld this way, but that's the way they did it. And you get to see a number of things. So let me play it again, and let's see what we see. So right now the current is circulating. You get to see some smoke, so something is getting hot. All right, I'm going to stop it here. What do you guys think is these squirmy white things coming out? Suggestions? No guesses? Yeah, it's flakes, but flakes of what? Impurities, scale, no impurities, no scale. And let me give you two more hints. It's no copper and no iron. So automotive sheet is typically zinc coated, right? To help with corrosion. Yes, that's the zinc. And that's the zinc that we're seeing that comes out. Zinc has a lot lower melting point than steel, and actually has a very low boiling point too, which is a problem because when the zinc evaporates can cause porosity in all kinds of welding. So that's what we see there. Let's keep going. But this is super cool. We start to see so many things, and at real velocity, you just see poof, a big spark and things flying all over the place. But see, look at all that is happening in this very short time. Here you go, the zinc coating being burnt off. Okay, which is not burnt, it's melted. All right, look how this area is changing quickly. All right, well, this lighter part here, that is the molten steel. And this is the miracle. It's melting. One electrode is on top, one electrode is on the bottom, and this is melting in the middle, right? And if there was any problem, if the melting started up here, that would be a disaster. Now, one of the reasons the melting seldom happens up here is because these electrodes are water cooled. So actually, this electrode is cold, the steel sheet is getting hot, we have a contact resistance here, so there is a big gradient of temperature between this hot center and the colder electrodes. And this gradient of temperature at some point goes through the melting temperature of steel. So you very seldom see, you have to do something really, really, really wrong to see the steel melting all the way to the electrode. Very interesting, very interesting. Really old video. When I came here, we had a resistance welding machine, and during lab renovation, somehow it disappeared. I miss it. All right, there you go. That's what is called a nugget. All right, so that's the way you weld cars. Now, there is another type of resistance welding that we do in this province, but this is done at industrial levels. This is not done at the shop of a random welder, because this is the way you make pipes. And it's called ERW, electric resistance welding. Can be with DC, can be with high frequency. Right, in this schematic, we have it for high frequency. And the way this works is very interesting. When you fold the steel sheet to make the tube, right? You have these rolls, and the tube is moving from the bottom left to the top right, and this is pressed. And now, in this case, the current is induced electromagnetically, but you can put also just contact electrodes, and the current tries to go from one side to the other side, right? But there is a gap, so the current to go from one side to the other, very often, it goes through here and comes back. So that's the whole point of the process. The current that is induced or somehow forced with electrodes is going to go from one side to the other, going through the V. And as the current goes through a V, we have a concentration of current, much like we have a stress concentration. there is a concentration of current. And here is a very hot point that melts. And as the tube advances, that melts and the rolls like squeeze it together, right? And in this case, also there is an amount of pressure and there is some, the impurities go away. So in this type of process, you don't protect the melt because you squirter out. The molten metal is expelled, very much like in resistant spot welding, although this is a very, 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 very different process. The fundamentals have some similarities. Filler material, you don't put filler material here. Polarity could be high frequency induction, that is the drawing we have here, right? These coils carry a current that is going in circles. The induced current wants to go in circles in the opposite direction, but it cannot jump because we have a gap. So the current goes around, it starts to go around, and when it collides with the gap, goes here through the tip of the V and comes back. There is something else that helps to do this circuit, and at this point I'm not very deep in my understanding, but they put this impeder, and this impeder modifies the magnetic fields such that the current always goes through this point here instead of finding some other path, for example, going up and down at different parts of the plate. So what are the characteristics of this process? Well, the cost per unit length is very, very, very low. You have a very high capital cost of installing these facilities that can measure easy 50 meters or 100 meters in length, like the setup for doing this type of welding. You need very expensive equipment, but once it's running, it can start churning out pipes at a very fast speed. It's typically used for making tubes, typically in carbon steels, but people have explored how to use it also for stainless. Typically, these are butt joints. And here's something paradoxical. This is typically considered a low quality, low cost process. So people would say that ERW pipe is never as good as a sub-arc welded pipe. And I am sure they say that for some good reasons, and it's probably even true. But the paradox is that in this type of process, because you do electric resistance heating and you move so fast, and what you melt, you squirt out. Actually, this process has a potential of being a very high quality process, right? It's quite paradoxical that people consider it low cost. We have a factory of Tenaris. I used to work for Tenaris way back in the night of the times when I was in Argentina. And they're a global company, and they have a plant in Camrose, okay, for making ERW. Applications, pipes for oil, for sure. Electrical conduit, when you see when people put like cables inside the little pipe, that is typically ERW. Pipes for hydroforming in automotive. If you look at a car from the side, right, you have the doors, and under the doors, you have this component in the car that goes pretty much from the bottom of the front fender to the front of from the bottom back side of the front fender to the bottom front side of the rear fender. And that is typically a hollow member that started as some sort of a pipe, and then is hydroformed. Essentially, they give it temperature and pressure, and they inflate it much like the way you do plastic bottles, but they do it with steel. Those pipes that are the starting point for making that component of the car is often is welded with ERW. Here you have a video that Tenaris put together about ERW. I think it's a video that is fairly artistic, and maybe is more artistic than it should in some places, but that's okay. Let's look at together, watch it together. That's the way you're trimming. All right. So ERW, as you saw, is like it's a way very specific for making pipes, and because everything is in line, you can do. In this case, they're talking the spray quench. They didn't show it, but there is a heat treatment furnace. Okay, I have a question. Terrifying. Well, some people make a living from working in those factories. I have not seen the one in Camrose, but I really want. How would you pick between some welding process compared to it? Okay. I have a question that is essentially the whole point of this course is, as a welding engineer, how would we pick welding processes? Funny enough, there's a section about how to pick a welding process in the Lincoln Procedure Handbook that all of you have or should be getting soon. And this is choosing a welding process is open-ended. There are better answers than others very often. And what do you base it on? For example, what material you need to weld, right? For some materials, for example, if you have aluminum, you're not gonna do subarc welding, so you can discard some, right? What thickness are you welding? So if you have something that is very thin, you're also going to discard subarc welding. But if it is very thick, likely you're gonna discard things like TIG. Right? And then another thing that matters is, what do you have in the shop, right? Because you might have something that is very thick, but you only have MIG and TIG, and you should be doing subarc welding, but you don't have one, and you might decide not to buy one. So your decision is influenced to a large extent by what do you have. Other thing is, how big is the job you have? I mean, if I need to make one thick section and I don't have a subarc welder, I might tough it out with MIG or TIG. Maybe I have so many, the job is so big that it justifies buying the subarc welder, right? That's a business decision. And there right there you have a decision that in the end has technical implications, but involves many other things. Another challenge, imagine you're running a shop floor with many welders. The welders might be all good welding with stick. And all of a sudden you decide, because you're so enlightened after this class, you decide everybody should weld with a flux core. And guess what? You might end up having a revolution, right? So if you want to use flux core, you might need to be very smart about how you introduce it, because you might have a workforce that is not familiar or not comfortable with it. So all those things, and some more go into practice. Sometimes the codes and standards say things. For example, in the US, until recently, you could not use MIG to weld bridges, period. Right? Because it once went wrong and people decided against it. For a while in our province, nobody wanted to use flux core because once they had bad experiences, and they banned it for many years. So you asked me a straight question about how you select a process, and I gave you some criteria, right? But it requires an understanding of the context and quite a bit of insight to make a good decision. It's not just based on small technical details. All right. So that's it for electric resistance welding. What I would like to share with you now is some processes using solid state welding. Okay, let's stop this share.